fruit by the
It's
foot.
going
Oh, okay. The way it's spelled. Okay.
They missed a chance.
Okay.
Yes.
Words. Okay. What's really nice about chapter 7 is how easy the math itself is. What's really, really nice about chapter 7 is how easy the math is, because literally you're just wanting to pick one of those two formulas. Why am I talking to myself?
I'm listening.
Yeah. I'm just wanting to pick one of those two formulas and use it. But what's hard is I have to justify why I get to use one of those formulas. Using those formulas, pressing normal CDF, or using those formulas and then going to a Z-curve is not that difficult. Finding the actual number answer, pretty easy. The hard part is why do I get to do it? So with the proportions, we discussed, and I think I called it the wrong thing because I've got dumb on you, which happens all the time to people. We discussed it was the law of large numbers, and we talked about that NP had to be greater than 10, and the n times 1 minus p had to be greater than or equal to 10, or was it 0.10? Again, I'm going completely blind lately.
You're doing your best. That's what matters.
It's 10. It's 10. Okay, so we talked about that, and you have to do that with, if you do that again, I'm going to throw something at you. We have to do that with proportions.
Who are you talking about?
Sally. I saw her throw things. If she does it again, I'm going to throw stuff at her. So we have to check these conditions first. But we also have to check the condition we checked yesterday, which was called, not the law of large numbers, but it was called the 10% rule. What did it say?
Said that the sample has to be 10% of the population.
Yeah, so as long as...
So we could do that. Like this class.
Right. Normally no, because we have such a low population. So this is different than the 10% rule. The 10% rule is back to my sample is less than or equal to 10% of my population. Now you have to check both these conditions for a proportion. You don't, for means, you only have to check the 10% rule. Okay, and I feel like we covered the means yesterday, and means are pretty easy. Means are actually way better than proportions, and let's talk about why today. Okay, so, why, Jesus? Why? Is it weird that I just want to teach sophomores and juniors because seniors get on my nerves? Like, discrete seniors get on my nerves for them 6, and then finally I get to AP stats, and then they get on my nerves.
Wait, which one of us was just getting on the
Seniors.
Yes.
The ones that were talking when I was trying to talk. Which ones were those? Which technically Shalia is a junior, so I mean she's technically not counting in that rant. Okay. Things we need to say today.
Samantha does not talk to me.
Well, that's true. Samantha's always an angel. It's like Ashley. She just gets thrown in when I clump them all together. So we were checking these rules in order to normalize everything. The whole point of my rant with that, because my God, that should be redundant. It's like the 4th day in a row we've done this kind of thing. The whole reason we check these things is in order to normalize, or in order to say this should be normal, therefore we can do the things with the Z-curve and saying these percentages. Otherwise, how do we assume normality? So we're doing all this to assume normality. You have to show you have a reason to assume normality before you can actually do the Z-score or if you're pressing normal CDF or whatever it is you're pressing. Before we can assume normal, you have to prove it. Yes, dear? Yes. No.
So we don't get punished for saying believe.
No. If you said I believe we can assume normality because, and you showed that math, I think that'd be a great sentence. But moving on. So what if and again we're assuming all normal populations, and then so they comes to this time of, what if we have a non-normal shaped population, which is what we were discussing at the beginning of class yesterday, because again, I just keep wanting to go big picture and I need to slow my roll down. We talked about people and salaries, about how if we did everyone's salary in the world, well, not the world, just America, it would be a very skewed graph because some people make ridiculous amounts of money, and therefore they mess up the whole mean. It's a skewed curve. It's not normal. Yet somehow when we take our sample and make our sampling distributions, we want it to be normal. So the reason that will actually end up being normal is by the central limit theorem. And this is pretty much the coolest theorem and like the coolest thing that stats has to offer. And it's actually an easy theorem to remember. So the central limit theorem, which, you know, normally when I hear theorem, I'm like, oh, Jesus, take the wheel, I have to memorize a theorem. That's actually not the case with the central limit theorem. It would be nice if you could remember the letters central limit theorem, like the CLT. But otherwise, the important part, as long as you remember, the sample size has to be bigger than 30.
How is that cool?
Literally, as long as it's bigger than 30, it will always be a normal distribution. Then we're never going to be able to, yes, we're going to have to do what we were doing before of showing that 10% rule, showing that, or it depends, that a proportions or a means problem. Because a proportions problem, we're still going to have to check all these things. And we can't even necessarily assume normality because if we fail that 10% rule, then we're just going to try to do math the way we've been doing it. But we can only assume normality if we've proven these rules, or we can actually assume normality when we're dealing with sample means if our sample size is bigger than 30. Which sounds like stupid, but seriously, like I just think that's amazing that even if we have something that's skewed, our sample will be a normal curve as long as our sampling distribution will be a normal curve, as long as our sample size is bigger than 30. And I can show you that in an applet, but it really isn't that cool.
So all we really need to remember is if it's our sample size is bigger than 30, it's approximately normal.
Yep. The sampling distribution is approximately normal. Again, there is an applet I can show you, and I'll post it in Google Classroom if you're interested in it. It's not that cool. Well, I don't think it's that cool. But literally, you can just change your sample size. Like, when my sample size is this, what does it end up looking like? And it can show you the larger the sample size, the more normal your data becomes. And then you're like, but again, as that rule said, there is too large of a sample size. Because, like, right now, if we took a sample size of 10 out of 13, that's too large of a sample size. So that's why a lot of statisticians have done this for a long time. And the perfect number where you can, like, just the right amount, you hadn't gone too far. I mean, of course, it'd be better if you did 50 or 100 or whatever, but at least 30. 30 people.
This concept,
Yes, dear.
what are the repercussions of having a sample size?
What are the repercussions for what?
Having a sample size that's too big.
We can't assume normality then.
Why?
Because we don't, well, it depends. Do we know that the population itself was normal? It depends. If we know the population itself was normal, then yeah, the sample, I mean, it's going to be normal. But what if the population was a skewed thing? Then how are we applying all this normality stuff to it? Because our samples are,
Wait, so
if this is our population, and we took a sample size that was way too big, is what you're saying, like, doesn't meet that 10% condition, then wouldn't you assume it would look like this as well?
So
And then it's not normal, so how can we apply all this normal stuff to it with the Z-score and the normal CDF?
why do we know necessarily because it's smaller it's normal?
because a lot of people have done this math just for a long time.
I mean, sure, so why isn't the bigger thing? I mean, if you'd assume a really big sample would be really normal, just because there's so many outliers, it probably ends up making some sort of.
Well, as we've learned, the higher the n goes, the lower the standard deviation, and that is true. So the less variability, which means the less of the ends, which means we're getting more of the center, which I agree with that. But again, back to, we assume our sample is eventually going to mock what the population was as a whole if our sample is that large. And if we don't know that the population as a whole is necessarily normal, then how do we know our sample is necessarily normal? So that's literally, that's all I can answer, is that unless you know for sure the population is normal, such a large sample size is a bad idea, because we can't assume normality for that sampling distribution.
I guess I'm just thinking, how can we ever assume normality? What, I mean, I know, 30 is a magic number, but I'm like, I guess it's from, taking some examples and they just decided, 30 is a good number. But like, is there any math that backs that up? Or,
Yeah.
I mean, obviously,
Yeah.
it's, but, like,
Yeah, Here's the whole proof of the central limit theorem, which is what you don't want to see from me. Yeah. Yes, dear.
So the CLT only applies to the sampling, not to the actual population.
Yes. So the central limit theorem is saying that even if my population is skewed, the sampling distribution will end up being a normal curve as long as my sample size is bigger than 30. But again, as me and Louise are debating, our sample size can only be so big because eventually, back to that 10% rule, if I have a sample of 30, then my population better be 300 or more. So if our population is small like ours, then none of this is even going to work. Okay, and you're like, why is this important? Again, back to the problem or whatever our situation is. Did it say in the problem that it was not normal? And if not, how are we able to assume normality? Because again, the math part's easy. It's just why were we able to assume normality? Yes, dear.
Well, does the population have to be bigger? Yeah, bigger than 300 for the whole 30 rule to work. Because if you had a population of 50, that's too big.
Yeah, it would have to be. Because you need to meet both conditions in life.
Right.
Yeah.
Oh, so the 10% rule applies.
Yeah. Yeah. So basically, if our population is not bigger than 300, why are we doing any of this?
So if it is, you can just have 30.
Yeah. Well, if our population is less than 300 and we know for sure it is approximately normal, then that's fine. But if our population is less than 300 and we're not really sure if it's skewed left, skewed right, and we're trying to say something about it, how are we able to assume stuff about our sampling distribution?
It's kind of weird. I mean, if you have the entire human population, you just chose 30 people. I mean, it's not 10%. But,
Yeah. No, but and again, the central limit theorem, I'm not saying it's not going to fail us. Of course, if you're doing the entire population, that's ridiculous. But it is important in the last paragraph because it lets us turn a non-normal population distribution into a normal sampling distribution. And so, like that picture showing, we're suddenly able to make inferences and apply a Z-curve and say probability stuff. But if the sample size is less than 30, we cannot say with certainty that the sampling distribution is approximately normal. Okay, so there is one problem for us to practice. It's on the next page. It's on the back. Okay, so how do I know this problem is a sample means and not a sample proportions?
Sample mean or sample what?
How do I know this is a p-hat? If this isn't a p-hat, this is an x-bar. Why?
Because it's a proportion. It has a decimal.
It's asking for a percentage.
Okay, so again, our whole goal yesterday, like on a free response practice problem, how do we know which formula to use in this one? What did they give us to give us context clues to know which formula to use? So what did they give us? They gave us the mean, they gave us the standard deviation. So which one are we supposed to be doing? Sample means or sample proportions? Sample means. We got so let's deal with sample means. So Lord Jesus, words are going to come out. Okay. In the coming week, your company will service 70 air conditioning units in the city. What percentage of the job will not be completed within 75 minutes? Show your work. Okay, well, first things first, we've got to show that we are able to do the math you and I want to do.
So is this on the curve? Is this going to be shaded to the left then? Because it's
Before we even make the curve, why can we make the curve? First things first. Why can we make the curve?
Does it say it's normal?
Did it say it was approximately normal? Anywhere in that problem did it say that we had a normal distribution? No. Okay, in fact, that genius noticing that, in fact, sadly, our population is right skewed. So we're already at a loss. We're going to have to use that central limit theorem, specifically because it told us the population was right skewed. They told us that we were supposed to expect to have a tail. So since we're not having that normal curve, the only way we can prove that we're able to apply that normal curve to the sampling distribution and the sample means is because we're going to use that central limit theorem. So the central limit theorem says we've got to have a sample size of at least 30. Do we meet that requirement?
Yeah.
Okay.
Is it 70 air conditioning?
Okay, so I'm going to say by the, and I'm actually not going to spell it out. I'm just going to put CLT, central limit theorem. If you want to spell it out, you can. If you literally just want to put, because 75 is bigger than or equal to 30, if you just reference the number in the central limit theorem, pretty positive they're going to give you the points for it. So by the central limit theorem, since 75 is bigger than or equal to 30,
Wait, are we doing? Oh yeah. Okay.
we are able to assume, yes dear,
Do you see the free response having to do with this?
yes.
Is the same like is 70 like I don't know.
It's like one of those that has subparts. This might be one of the subparts. One of those that A, B, C. Say Mackenzie, say yours.
I think it's 7. Like I don't.
70, yes, sorry, I meant 70. Yes, we were doing 70 air conditioning units, you're right. So, okay, so by the central limit theorem, since 70 is bigger than 30, because our sample is size 70, that's the N, and 70 is bigger than 30, we are able to assume normality. And now we can do the math you and I want to do. But until we actually show that, or have some sort of proof, we can't actually jump into the math you and I are wanting to do. Okay, so we know that our mean is supposed to be what?
An hour.
60 minutes.
We're going to leave it as hours, but yeah, we could convert all to minutes. We might have to in a second. She's right.
Yeah.
Okay, and as for our standard deviation, we're going to do sigma over the square root of n. We're told that our standard deviation is 1 hour, and our population is, our sample size is 70, so 1 over square root of 70, which is,
It's like 1.
0.1, I think that's right. Is that right?
0.12.
Okay, cool. So, and again, Miss Compton likes to draw the picture. If you don't want to draw the picture, it just helps me think things through. So, 0 is here. We're at 0.12. That's not very far away. And so, that's good.
That's not good. One standard deviation.
Like I was saying earlier, since it says what percentage of the jobs will not be completed within 75 minutes, so is that everything shifting to the left?
Makes sense.
That makes sense. That makes sense. And then Miss Compton stinks because we've not checked one other thing. So again, I'm assuming that I can do all this math, and I did put my sentence about the central limit theorem, but what else did I not check?
The large numbers there.
This 10% thing. So, and then we can call it the 10% rule. I don't really care. Again, 10% condition is what the book calls it. By the 10% condition. How big is our population?
All of the air conditioning units in the city.
Okay, so we're having 70, so 700, definitely, so we're definitely servicing more than that.
This is
So-
at least how it's- so-
There are definitely more, air conditioning units in the population. I knew I knew words. Yes, dear.
I know you're gonna make fun of me for asking.
No, I'm not.
But I just wanted to like quadruple check. Is it higher the population, lower the standard deviation, or higher the sampling size?
Higher the sample size.
Okay. So if two places are both like, or if there's two populations, and one of them's bigger, but they have a smaller sample size, the other one's gonna have the lower.
Where if we want to deal with the same population, like if we did this exact same problem, exact same scenario, but did a sample size instead of 70 air conditioning units, we did 80 air conditioning units, that would increase our n, which would decrease our standard deviation, which would therefore decrease this denominator, which would make this more approximate.
Okay, so but like if this was the exact same sample size but a greater population, does that affect that at all?
How big of a, they'd be hard to compare. It depends, are they the exact same size population?
For example, the reason I'm asking this is because I saw this and I got curious.
Okay.
It says that they took basically the population is 1,700 people, or the sample is 1,700 people,
Okay.
but the population is 34 million.
Oh, Lord.
And the other one's a sample of 1,000 people, but the population is 1 million. So which one's going to have the greater standard deviation?
The greater the standard deviation, it's going to be the one that has the smaller population but the larger sample size. It had a small sample size. The second one you said, where it was not as many people, but they still did 1,000.
Yeah.
It's going to be that one.
Okay.
Okay, but anyway, so we wrote these sentences, and seriously, we wrote the sentences so we could do this math. The math part was easy. It was just proving we could do the math. That was easy. We have that the distribution is therefore approximately normal, and we want to find that p is bigger than that. So I want to do a z-score, and I've done this wrong. I don't know why I put that. That was stupid of me. I want to find my z-score. I like doing my z-score. So I think we're supposed to do 75 minus 70 over that standard deviation of 0.12. And now my life actually feels like it's back on track. Don't know what it got into me there. Trying to make things happen faster than they are. Again, this math is easy. We were given this. We had to calculate this because it changed because of our sample size. Now I've converted it to a z-score, and my z-score number would be 0.83, which is still a good z-score number. So if I did draw my little thing again, 0.83, that's still a good thing. You don't actually have to do a z-score. You could be like Hunter and do normal CDF. If you do normal CDF, you don't even have to normalize it. So he's doing his lower, his upper, his mean, and his standard deviation. His standard deviation was 0.12. His mean was 70. His lower was 75. His upper had a bunch of zeros. Yes, dear?
5 divided by 0.12 is not 0.83.
Yeah, I don't.
That's not it.
Yeah, I don't feel right about it.
Did you just use the other standard deviation or something?
No, I didn't feel right about it. I didn't type it in. I was guessing things. Someone calculate. Where is my calculator?
It's going to be a big number. Yes.
I was so excited that I thought it was a good number.
70 isn't the mean. 60 is the mean. 70 is the number.
I mean, that's even a bigger
Yeah,
number
that's an
than
even bigger number.
100.
Woo! And that would be Miss Compton being dumb. Okay, I love it when I'm dumb. Don't you? It's just so great. It makes my whole day when I'm dumb. I feel stupid. Okay, my standard deviation is fine. That I can actually calculate. Woo! I'm not incompetent with that. However, what's supposed to go in the numerator when I'm doing a z-score?
The value and the mean.
Okay, and what was the mean? Was the mean 70?
1 hour.
It was the 1 hour, or so it's either going to be 60 minutes or 1 for 1 hour. So I'm doing something with a 1 there.
Does it have to be
75
more? Would it
minutes.
work the same
Okay.
as it did minutes?
It's going to work the same if you do minutes. If you do 75 minus 60, you still should get the same answer as me.
So 1.25. 5 minutes.
It's 15 minutes over the hour. Isn't that 1.1?
So 1.25 because it's 15 minutes, and 15 minutes is 1/4 of an hour.
0.250. So yeah, okay.
That's an alright z-score.
That's like 2.
Okay, but I'm with Kenzie of maybe I didn't want to convert it all. Maybe I just did 75 minutes minus 60 minutes over my standard deviation.
Wait,
That's the
different
huge number
numbers
still.
now.
Yeah, I think you have to keep it in hours, but that's a huge number.
We could do it and then divide by 60.
I mean, yeah, might as well just put it in hours at that point. It's already hours.
That's true.
Yeah, it's not,
That's true.
you know,
I feel like You're fine. No one was even noticing you. We were still in this world. Miss Compton messed up the math today, which is not the first day she's messed up math, sadly enough. First today, but not the first day. Sometimes I'm genius, sometimes I'm not.
I think you're always genius.
I appreciate that, and I love the like dead silence after that. That was my favorite part.
But everyone started laughing, but I said, I think you're always genius, and then under my breath I'm like, bonus points.
Oh.
But I still think you're smart.
Okay, I know what Kenzie was asking. I then divided by 60 to convert it back to hours, and I can still make it the 2.08. Louise is technically right. We should go with what they're giving us to begin with.
Yeah, but they give us 75 minutes.
They do, but they told us hours. You would think.
You have
Okay,
to
let's
multiply
roll
the
with
standard-
together.
You have to multiply the standard deviation by 60 then, because the standard deviation is measured in hours, so you have to multiply it.
But the standard deviation, the Z-score is supposed to be unitless. I thought the whole point of going to the Z-score was because it was
Z score is
unitless.
unitless, the standard deviation isn't.
Oh, that's true.
Yeah.
Annoying as hell.
Yeah, but it's 70.
So it's minutes, 75 minutes, is the minutes cancel out. Or I guess hours of hours.
Oh.
Either way.
Oh, I know why. Sorry. He's making life way too deep. That I got the easy answer. Why would the deepness?
Because he does not.
Why would the deepness lie?
Okay.
He's trying to make life way too deep. I'm being stupid, but he's trying to make life way too deep. When we did this, when we did 1 in the numerator there, wasn't 1 in hours. Wasn't that in hours? So we have already done our denominator in hours. So we need to stay in hours. If you want to change, you need to change that denominator into minutes as well. So if you're wanting to change things, you could do 75 minus 60 in the numerator, but in the denominator, you would need to do 60 divided by the square root of 70.
So, like, in the beginning when I said we can change it to 60 minutes, like, if I would have done that, it would have.
Yes, if you had changed everybody over to minutes, it would have been fine. But because I had already committed to hours, I need to stay committed to hours. Lord, blindness kicks in like a mofo. Yes, so if we've done, I know, it's bad today. If we've done hours, we're going to stay hours. If we've done minutes, you can stay minutes. You just have to be consistent. So in the middle here, when I tried to mix and match, no wonder life went terribly. Absolutely terribly. Okay. So I like Z-scores. I thought. I don't know. I'm having a day today. So I would have done this and then looked at my table and figured out my percentages. You can't see numbers. Right. Is it?
Yeah, well, it says.
Greater than. Not be what percentage of jobs will not be completed within 75 minutes? So they took longer than 75 minutes. So wouldn't it be everybody else?
I don't know.
Yeah.
I give up now.
No. Don't give up now. It said in the problem at the last sentence, what percentage of the jobs will not be completed within 75 minutes? Isn't this mark for the 75 minutes? So everything under this mark was done in less than 75. So we're wanting to know higher than 75. You're overthinking your life. Okay, and after we do this, you should end up getting... I look at my Z table. Where are you, Clark? I don't know what words you said, but I know they weren't helpful, were they? It was.
Correct.
Ew.
But still discriminatory.
0.2? Did you get 0.2? I got 0.2.
I am
0.2033.
so trying to do things.
Okay, well, when I looked at my table at 2.08, I got 0.9812. And so, since that's for the left of the curve, I did 1 minus 0.9812. And I ended up getting 0.2033.
That is definitely not what my calculator was trying to do.
Now, if Hunter is insistent on his normal CDF self because he hates the Z-scores, which is fine, he's got to make sure, again, we've got to be consistent. So hopefully for his mean, he did the 1 hour. hopefully. For the lower, he did 1.25. For the upper, he did a bunch of zeros. And then for the standard deviation, he did 0.12.
That gets me 0.018.
0.018.
Yep.
Do it again.
With the lower is 1.25, upper a bunch of zeros, mean 1, standard deviation 0.12.
1.25. Mean 1.12. 0.18. Okay, cool. I'm cool with that. 1 minus 0.9812. Yeah, it would help if I could do math today. Okay, Hunter and I agree. I just can't write. Okay, so Hunter did normal CDF. He typed in these things. He got a 0.0188. I did my Z-score, figured that out, and also got the same numbers as him. I swear to goodness, I'm just being blunt. Whoa. So 18%, that ends up being 18.8%, which is about 20% if we're going to lie, or 18.8 if you want to.
Wait, what? No, it would be 1.88. 1.88%.
Oh, duh. Jeez Louise, Miss Conant.
Because Louise.
Okay.
It's Lewis.
So we're feeling good about this.
No.
Oh.
What are you?
Okay, somehow we got off track, but we're gonna get back on track. I swear to goodness, we made life way too hard. Chapter 7 is like the easiest of the chapters. The math was not bad. It's just Z-score jump.
At the beginning of all this, I asked you how you felt about it. You said maybe super easy.
Our words would say 1.88, about 1.88% of the jobs will not be completed within 75 minutes.
Exactly. Okay, so Kenzie, God bless her soul. If she wants a piece of my emergency chocolate, I'll give her. Hold on a second.
$5. If you want to profit now.
Kenzie, God bless her soul, got us back on track. Say the words again, Kenzie.
When you go back to the
1.88. Oh, the words.
1.88% of the jobs will not be completed within 75 minutes. Before you were rounding to like the nearest percent, is there a reason you're keeping it 1.88 or?
No, I was just trying to jump up to 2 or say something smart. I don't really have a reason.
Okay.
I mean, it's probably smarter to reference your exact number to 2 decimal places. It's just when people say percentages, do they normally say 95.7? No, they normally say like 96. So it's okay if you 1.8 it, but it's also okay if you say 2. And it will not be completed. Okay, so we made life way too hard yet again today, and I swear to goodness, I was like just talking to somebody about how great this chapter is, if only we didn't have to use words. If this was not an AP math class and you did not have to use words to back yourself up, my gosh, all you have to do is figure out, is it a means, is it a proportion, apply some sort of Z-score, figure out some sort of percentage, and you're done. The hard part is the words. So in my mind, there are 3 parts to the words. I thought this through a lot, and I think there are 3 parts. There's the math part, step 2. That's normally the easy part. Like, I can do math. Well, question mark today, but I normally can do math. That's the easy part. Part 1 and 3 are the hard part. Part 1 is, why do you get to do the math? So, like, proof for math. Why do you get to assume it's normal? Why are you getting to say these percentages? You got to have some sort of proof to back up why you get to do this math. And part 3 is bad because now that you've done math, you got to say math. I'm going to say math applied. You've got to take the math you did, take your percentage, and reference back to that stem. Now that I got 1.88, what does that mean in life? Which is the part Kenzie's good at. Okay, I did not think that one was going to take that long. That is so sad. Let's look at that thing the one that has the trains and the stupid, what are the hobbits? Come get this. You can have two squares. Okay, let's look at the trains and the hobbits. I want to talk about them one stinking last time, and I want to move on with my life. I don't want to talk about trains or hobbits. I want to talk about the problem on the next page. So much. So much.
I guess I shouldn't be allowed to.
Probably not. Okay. So example 3 is similar to a problem on our previous free response problem. Jesus, take the wheel. How do I know it's a means problem and not a proportions problem? Okay, and then they ask some questions. Should they be concerned? Something about a birth weight. Can we assume normality? So if we're going to do math in really the 3 steps, can we assume normality? And if so, why? So I'm going to abbreviate it. CLT, 34, bigger than 30. Okay, and then what else do we need to check? There's also something else besides CLT. Okay, 10%. Let's see. 10 times 34 is 340. How big is our population? Yes, and we're talking about special groups living near factoring babies born to mothers. Do you think there's more than that in babies? So there's certainly more than 340 babies. So yay, we used words, and that now we can assume we have normal. Maybe I should throw that word in there. Therefore, normality.
Why are babies such a common topic in statistics?
No. I'll round it. If I would, I'd get rid of them if I could. Not babies, but probably not. Lord. Okay, we know our mu is the mean given, which is 7.8 pounds. We need to figure out our standard deviation, which is going to be that over the square root of n, and our sample size is
Thank you.
34. God bless you. So it's 2.1 over square root of 34. I need to know what that number is. Hunter, quickly.
34.
I want to finish this before I leave. 0.36. Okay, that's my new standard deviation. So I'm wanting to convert to a z-score. So I think we're wanting to know 7.1. So 7.1 minus 7.8. Yes, I know that's negative. It's still okay. Over 0.36. And I'm going to end up getting a certain z-score, which is... Hunter's doing his thing. Negative 1.94, which is almost 2 standard deviations away from the mean. So we could almost try to use that empirical rule and not actually have to do math, but Hunter doesn't mind math. Let's do it instead because we like Hunter's way because we're lazy, which is fine. Normal CDF, lower, upper, the mean, the standard deviation. Now it really might help this time to draw us a stinking picture because if we're at 7.8 as the normal mean and we're down here at 7.1, we've got to be careful when we think about which way. So they said, suppose a group living here in the area have a mean birth weight of only, so everything less than that, yeah? So our lower is actually going to mean the negative something with a bunch of zeros. Our upper is the 7.1. Our mean is 7.8. Our standard deviation is the 0.36. When he types that all in, while I'm looking at my curve to see if I can beat him, I get 0.0262. What do you get, dear?
0.026.
Ah, how funny. So I looked at my curve at negative 1.94. I got 0.0262. 0.0262. And he got 0.026. So that's really 2.6% either way. And so finally we could use the words, should they be concerned?
Probably.
Probably yes, if they fall within the lower 2.6%, it's
Kind of low.
not good.
Probably because of that, yeah. So you're somehow going to say 2.6 and reference the concerned,
Big
and then we're done.
Thin boy.
Again, the math part's easy. It's just hard are you in your words. Tomorrow, Jackson gets his way.